Okay, so in this video what we're going to do is we're going to go over the history of HCI. There is a chapter in the Scott Mackenzie book, so if you've not read that, that's going to give you a lot more detail. So what I'm going to do in the next period of time is I'm just going to give you more of an overview, and then if you want the detail, you can go and have a look in the book or do a little bit of further research on your own. So the first thing I have is just a brief 5-minute video, and that should hopefully give you kind of a sense of how computing has changed over time and what that kind of means in terms of how people operate it. And that'll link into the human factors stuff that we'll talk about as well.
The invention of the computer has been one that has allowed mankind to push the boundaries of what our minds are capable of. With advancements in the field of human-computer interaction, these technologies are becoming available to more and more people every day. These advancements are opening up the world of computers to people who are young, old, and those with disabilities. However, interacting with computers was not always so simple. An early example of basic HCI can be seen in one of the first computers, the ENIAC. In order to be used, a team of multiple people were needed to physically plug cables into different parts of the computer. Because of this need for multiple people, coupled with the ENIAC's size and speed, the idea of personal computing was still inconceivable. The next major advancement in HCI came from Ivan Sutherland in 1963 with his invention of Sketchpad. Sketchpad, along with the technology of the light pen, were the first steps in creating graphical user interfaces as we know them today.
Command the computer to draw a line. It will draw a line from this position where I am now to any subsequent position of my light pen. This is much like a rubber band stuck on 2 pins. One is nailed on the screen here, and the other is at my light pen.
Arguably the most impactful invention in HCI history was first introduced by Doug Engelbert during the Motherwell demos.
I don't know why we call it a mouse. Sometimes I apologize. It started that way, and we never did change it.
The genius of the mouse lies in the fact that it can be first used and understood by anyone in a matter of seconds. The next invention that brought the most freedom to computing was the touchscreen and stylus. This is an extremely intuitive way to interact with the computer. However, the stylus still obstructs ideal interaction.
We're going to use a stylus. No. Who wants a stylus? You have to get them and put them away and you lose them. Yuck. Nobody wants a stylus. So let's not use a stylus. We're going to use the best pointing device in the world. We're going to use a pointing device that we're all born with 10 of them. These are fingers.
Multi-touch control has been the biggest breakthrough in HCI because it gives us the freedom to interact with our devices the way that our minds work best. This concept can be understood by people of all ages and literally brings the power of computers to our fingertips. Elderly who feel as though they may be losing some of their freedom are now able to gain more in the digital space. In addition, the learning experience is being enhanced for many children who now have the freedom to explore the internet on their own with the simple touch of a screen. However, touchscreens are simply the beginning. Every day we're seeing more and more technologies that allow us to use our eyes, brains, and voices to interact with the devices around us. With each of these inventions, we gain more and more freedom to coexist with these devices in our personal lives. Some of the most groundbreaking work is being done through the technologies of eye tracking. Eye tracing works by allowing the user to move the cursor on the screen simply with the movement of their eyes. With With the use of this technology, computers are becoming available to many people with physical disabilities. And while we may be used to what it's like to have a computer talk to us, we're just beginning to learn what it's like to have them talk back. Alexa, open the pod bay doors.
I'm sorry, Dave. I'm afraid I can't do that. I'm not Hal and we're not in space.
Okay, so a nice kind of interaction there on what sort of things might be possible. Of course, now is the time I have to like relearn how to make Google work. Let's try that again. It's over there. Okay, so what that should have kind of given you, I guess, is a sense that, you know, computing is now, you know, what's possible, right? Loads of things are possible with computing, whereas before we were somewhat restricted by technically what was possible. Now those limitations are becoming less and less, and the types of interactions that can be afforded are, you know, not endless, obviously, but they're becoming much more varied. So, what do we mean when we talk about a human and we talk about a computer? So for a long time, humans were known as computers. And so in the early days of computers, what you had was effectively very large calculators that were operated by people, typically women. And so you had things like the IBM, early IBMs from the late 50s, early 60s. They cost millions of dollars. So if anyone hasn't seen, this movie is very impressive actually when it comes to kind of considering society's input on the role of computers and what is a computer and how does technology feed into our society. So the story of Hidden Figures is a bunch of women who were known as the computers. They worked in NASA and they did a lot of calculations by hand for the space race and so on. But in doing those computers by hand, I mean, these were very intelligent women doing complex mathematics and, you know, very, very quick arithmetic on paper. And then they discovered that they could use computing, use the power of computing to make their lives easier. And of course, was that the start of, you know, computers are replacing people? Well, yes, computers replace people, but obviously people adapted, people created new skills, and so some of the earliest programmers of computers were in fact these very intelligent individuals who were behind the introduction of them. And they didn't see them as replacing them, they saw them as improving the quality of work and the speed of work that they were able to output. Yeah, so Hidden Figures, if you've not seen it, get hold of it and have a look. Very interesting. Okay, so before that though, how did kind of the concept of these computers and the ENIAC exist? So Vannevar Bush was an advisor to President Franklin Roosevelt during World War II, and he first of all wrote this essay, I think it was for a newspaper in 1945, and he was focusing on what would be the potential of this new technology that we're thinking of and how would we use it for good. So how could we take his view of a technological world and ensure that, you know, it would ensure peace and it would give everyone the information they need to maintain that peace after World War II. So what he had was this kind of conceptual view of how the brain works and could computing work in the same way. So in the brain, you have different memories that are connected into groups. They're related to one another. So if you remember something about early school, you might remember the house you lived in, and you might remember the name of your teacher. And all of these things, of course, are related only by your experience as a person. So could a computer take all of that? So hyperlinks, as we know it, is that connection between two pieces of information. How are they related? Well, we have data structuring, data indexing, in a big way now. But in the early days, it was basically a couple of pieces of information and connected. So this essay was reprinted later on, after, as the internet came to fruition. But this was the early idea. To think that the early idea for that came as early as 45 is quite cool. So that essay you can download. You can go and find it if you want to have a look. Some of the language is actually really interesting. Okay, so from that idea, we have the ENIAC. So the ENIAC was created around the same time in 1946, and it was created in the University of Pennsylvania, and it was part of the war effort. So the role of it was to do calculations for hydrogen bombs, and Monte Carlo simulations, which are ways of determining statistics without data. So if this was for the war effort and it was there, how was it used? Well, you had to go to it for a start. It was massive. It took up a whole room. It weighed 27 tons, so there was no taking it anywhere. And so the very first computer you can see, actually, if I find my mouse, you can see all these cables that are connecting things together. And if you think back to very, very early telephone exchanges, it was the same principle. Way before kind of hard drives and holding things in solid state. It was connected. There was bits of paper and cards that were used as programming methods. Following on from that, we get to 62, and Ivan Sutherland, he is looking at how you can create shapes on the computer rather than just programmatically coming up with them. So what he created, I've got a little demonstration of it in a second, is he created something that would allow him to use a light pen, which he's holding here. You can see it's all wired, so it's all connected and it just goes in way up here. And what he did was he would press on this keypad that he has in his left hand. That would lock in a coordinate, and then he moves the light pen to a new position, and it draws a line between those two positions. So very basic, drawing a line, and then, or as we would think of it now. You can then press it again to lock in a second point, and so on. So what you have is almost a stack of positions, and it draws a line between them. It probably took a hell of a lot of memory to do that anyway. So this is the demonstration.
Hello, I'm John Fitch, MIT science reporter. We're at MIT's Lincoln Laboratory in Lexington, Massachusetts, a major research organization which has played an important role in developing this nation's defense system since World War II. And although Lincoln Laboratory is perhaps best known for its work in radar and advanced warning systems, it has also seen the beginning of the computer era and has made many important contributions to it. To learn about some of its recent work in improving the relationship between man and this important machine, we talked with Professor Stephen Coons, an associate professor of mechanical engineering at MIT and co-director of the Computer-Aided Design Project.
John, we're going to show you a man actually talking to a computer in a way far different than it's ever been possible to do before.
Surely not with his voice.
No, he's going to be talking graphically. He's going to be drawing, and the computer is going to understand his drawings. And the man will be using a language, a graphical language that we call Sketchpad, that started with Ivan Sutherland some years ago when he was busy working on his doctoral degree. And you will see a designer, effectively, solving a problem step by step, and he will not at the outset know precisely what his problem is, nor will he know exactly how to solve it. But little by little, he will begin to investigate ideas, and the computer and he will be in cooperation, in the fullest cooperation in this work.
Well, now, how does this differ from the way the computer has been used in the past to solve problems?
Well, the conventional way, the old way of solving problems with a computer, has been to understand the problem very, very well indeed, and moreover to know at the very outset just exactly what steps are necessary to solve the problem. And so the computer has been, in a sense, nothing but a very elaborate calculating machine. But now we're making the computer be more like almost like a human assistant. And the computer will seem to have some intelligence. It doesn't really, only the intelligence that we put in it. But it will seem to have intelligence. In the old days, to solve a problem, it was necessary to write out in detail on a typewriter or in punch card form all of the steps, all of the ritual that it takes to solve a problem.
Because the computer is so literal-minded?
Because it's very literal-minded. If you, for example, in the old days, made so much as one mistake of a comma in the wrong place or a decimal point that was omitted, the entire program would hang up and wouldn't run. But nowadays, if you make a mistake, you can correct it, as you'll see, immediately, and the computer is much more tolerant and much more flexible.
We met next with...
To do this, I must first indicate the center of my circle.
Yeah. So I'm just going to move it on and let you see the end of the actual demonstration, just because 19 minutes is a long time. So.
In order to do this, I must first indicate the center of my circle. Let's choose it to be here. And then I'll move out to an initial radius, let's say this point right here, and I press the second button to start drawing the circle. Here's our circle. Let me reduce the drawing slightly so our circle shows on the computer scope. And you see as I move the pen, it's ignoring the radial position. I've just gone off the scope screen here. The radial position of the pen, I'm only looking at its angular position. So I can
be very sloppy as you like.
Right. In other words, the computer has supplied the compass here, much like it supplied the straight edge for the straight line.
If you go backwards, you erase it.
And I can wind it up the other way. Now, if I tell the computer to put that point right at this circle, right in that point right there, the computer knows that those must be connected. It turns out that they're not really connected. It's a very small nub there. Let me move this away and show you that they're really not connected.
Yeah, okay, so that gives you a sense of, what the sketchpad can actually do. So that was in about 62. So sometime before 65, probably 63 has been the most credited. And this was at Stanford, so a lab, very well funded. So again, defense. So the university, the United States Department of Defense was funding, at the time, a lot of technology development for the armed forces. Them and NASA. NASA still do a lot, and very publicly. The United States Department of Defense obviously is still doing it, but they don't publish as much as they used to. So anyway, he's got funding from NASA, he's got funded from the Department of Defense, and they're trying to come up with new ideas on how people use technology and how they can use technology. So Doug Engelbert was super motivated by the Vannevar essay, and he kind of used that as his motivation to work towards building the XY position indicator for a display system, or as we would learn to call it, the mouse. So there was a conference in 1968, and 1968 is when the mother of all demos happened. So this was probably the first demonstration of this new technology live in a public area, and it was then used in computing terms in a very short period of time with the Xerox Auto, which was released in '73. So not a lot of space in between that demonstration and its inclusion in the new tech. And alongside that, he published what would become the first comparative study in HCI. So that comparative study is super important. So the book has a whole bunch of information about it, but essentially he was replacing a position indicator, which would be a pointer, so a laser pen. And his idea was that it would be pointing at a position. That's why the arrow on a mouse is called a pointer. Not an arrow, it's called a pointer. So he compared people selecting things, pointing at things, and he looked at how accurate they were, he looked at how long they took, he looked at fatigue, and this idea that you could do what you would normally do with using almost your whole arm to point at things, but instead you could just use your hand on the mouse, was the basis of that very first comparative study. So this is just a demonstration of that first one, which I'll show, but also Doug Engelbert also gave a presentation and talks at Google, so if you have time, go and watch that. It's very interesting, kind of hearing from his point of view how this came about. But here is the demonstration of the mouse.
Okay, to talk about control devices, we'll use this overhead camera shot where you can see the devices that I'm using. I use 3, and they're not all standard. We have a pointing device called a mouse, a standard keyboard, and a special key set we have here. And we're going to go for a picture out in our laboratory in Menlo Park and pipe it up. That'll show you from another point of view more about how that mouse works. Come in, Menlo Park. Okay, there's John Andrews' hand in Menlo Park. And in a second we'll see the screen that he's working and the way the tracking spot moves in conjunction with movements of that mouse. I don't know why we call it a mouse. Sometimes I apologize. It started that way and we never did change it. Right. As it moves up or down or sideways, so does the tracking spot. And the principles for its operation are quite easy to see. You'll turn it over, Don. Can you hear me, Don? If you turn it over, we'll see. Right. Its principle is that there are 2 wheels that roll on the surface. But since they're right angles and kind of sharp edges, one roll and a slide in one direction. Each of these wheels controls the potentiometer, the voltage output, sampled by an AD converter, the numbers taken in by the computer at sample times as to what the horizontal vertical components are to be of where it should put the tracking spot. And as the mouse moves over a surface, then each of those wheels either slides sideways without rolling or rolls an amount that very closely duplicates the particular component of horizontal or vertical in the net motion it makes.
Yeah, so how cool is that? Like, did anyone notice that the mouse is upside down to what we would normally consider it? Like the cable's coming out the bottom towards the user rather than away. And so, interesting point. But what's interesting is that it is effectively an Etch-a-Sketch. It's got 2 potentiometers, one moves something up and down, and one moves something left and right. So the concept of having the potentiometers to control movement is not a new one, right? Etch-a-Sketch came out, what, early 60s? So the fact that this is an example of someone who's taken existing technology and applied it to something else. He's taken this existing concept of 2 potentiometers that can control one point of movement, and then he's applied that to technology, taken the data from those potentiometers and put it on the screen. So that is the demo. You can see some more footage of the demo online and so on, but the main thing I want you to go away and have a read on is that comparative study. Have a read on what sort of things he's comparing and trying to show, and we'll talk about that a bit later on. So at this point we have, we've established that computing is a thing. The Xerox Alto was obviously early 70s. But at this point, there's still, the idea of personal computing is still a bit out there. There's no sense that people can have their own computer. Although they're becoming smaller, they're becoming manageable, they're becoming a potential household item, they are still very expensive. And then IBM came along, and IBM created the IBM 5100. So this is a common theme of you'll see of computers, particularly IBM, of their kind of numbering system for computers. The bigger the number, the better the computer. But in 1975, they created this. They created two portable computers. There was the 5100 and the 5155. So you can see there's a difference in spec in terms of RAM, a tiny amount of RAM, right? That's kilobytes. And a megahertz processor. Compared that to, you've probably got like 1 gigabyte of RAM for an entry level computer right now. So huge, but at just under $4,500, they were marketed at business professionals. And the idea was that you would take this portable computer with you, so you can take your work home, because you can't take files home. And lots of kind of business professionals, your guys in finance, your sales guys, they're going out and they've got file after file after file. And that's where IBM was aiming this at people who carry. Why would you carry all of those files when you can just carry a computer? Well, we have one in the computing department, and I can tell you that a box of files is lighter than the portable personal computer. So this little keyboard would just flip up to cover the screen. You can see space there, 2.5-inch floppies, manual contrast controls, all that sort of stuff. And of course, it's all command line interfaces. So for the convenience of leaving behind all your files, you get to learn to be effectively a programmer of the generation, because you get to do command line interfaces. So all of those issues with command line interfaces that we know of exist, right? So you have to remember information. If I don't remember the command, how will I find it? I have to have a book, I have to go and find someone, but it's a long process for me to get all of the commands. I can't really explore, because what would I'd just be typing random things in to see what happens. I can't really undo. I need to know the command for the alternate action. So if I want to move something somewhere, I need to know the command to move it back, rather than just undo. It's not interesting to look at. It's often not formatted very well, that output that comes out. But this is what people, mid-70s, you can buy yourself a portable computer, you can take it home to the family, and it was very much an executive toy. Fast forward a little bit and you get to the Xerox Star. Now, the Xerox Star was the first commercial system to use a desktop metaphor. So there were Windows icons, menus and pointers. So you can see we've got the mouse there, it's got now 2 buttons on it. It's now the way you would expect a mouse to be. So we have Windows here. So I've got like a word processing document open on the screen. There are icons, which would be all of my files, folders. There's menus, so I can click on menus up the top to get features and functions. And there's a pointer, which is my mouse position, is visible to me. So that, and what you see is what you get, which is this idea that what's presented on the screen is what is possible. If I can't find it in a menu there, it's not possible. So I don't have to remember suddenly all of these facts and commands in order to be able to use things. And so this was touted as one of the first kind of personal computers. Everyone in the office can have one. Yes, they were expensive, but they were sold on, oh, think how much money you'll save if everyone has these things. Now Xerox, there is a quite lengthy paper that details all of their outputs, all of their research, all of their processes of user-centered design. So they were the first company who really went out and asked, what do you need? And can we make it? Can we use this revolutionary new idea? They beat IBM. They created this commercially available personal computer, but it was a commercial failure, and that was due to primarily issues with the hardware. So if you had a reasonably large file, it could take you a couple of minutes, and that's just a lot of downtime that companies cannot have. They weren't reliable enough to maybe work on files for a long time. People were losing data, so that's why the Xerox Star commercially was a failure. But in terms of HCI and progressing modern technology of the time, it was an absolute success. So that was 8-1. So there's, at this point, background brewing of people who are interested in human-computer interaction. They're interested in how we are using these new technologies that are suddenly finding their way into the workplace. And they had the same problem that we've always had with change, right? That was a massive change, so the change management process was huge. But researchers decided now's the time that we should get together and we should start to form an organisation that will help us to monitor and improve this development. So enter ACM SIGCHI, so the Special Interest Group for Computer-Human Interaction. It's an American thing. They say often CHI, C-H-I, versus we would say HCI. But CHI is now the generally accepted term for a conference. So every year, the Special Interest Group for Computer-Human Interaction has a conference called CHI. So the first conference was in 1982, and the figure shows that the amount of papers that were submitted and that were accepted were small. So over time, that's grown and grown and grown and grown. But what's quite interesting is that the acceptance rate has stayed reasonably the same. Conference 2017 acceptance rate was 25%, and that's not unusual. More and more and more papers are being submitted. It's often in interesting places too. So this year it's in Hawaii, next year it's in Japan. Last year over 5,000 people attended this conference. It was held in Glasgow, and the only place that could hold that many people in Glasgow was the Exhibition Centre. So that's the scale of it, right? That's a football match worth of people showing up to see advances in human-computer interaction. So it's big business, and we will talk later about that paper submission process and kind of the research group behind it. But if you go away and look at the ACM, they have a whole bunch of SIGs. So they have special interest groups for accessibility, which we'll talk about, but they also have groups for very specific things. If you're interested in data, and it's not just HCI, ACM is all computing. So artificial intelligence, machine learning, robotics, networking, all of these things. But obviously we're interested in the SIGCHI. And if you're looking for interesting things to read, you can go to dl.acm.org on any campus computer. We have institutional login for it. And go and have a look at the most recent conference and the sort of things that people are looking at, and you'll see not only how varied they are, but also how strikingly specific they are. So people might be looking at something very, very specific, a small part of a process, but it's all contributing to knowledge. So it's all worthy of publication. Okay, so first conference, 82. Following on from that, there is the publication of a book by Card, Moran and Newell. So that is not the same Newell that was an ex-professor at Dundee. That's a different one. And they were basically interested in the psychology of HCI. So for anyone who's interested in the human side of HCI very much, or the cognition, this is the Bible. This is the book that has everything you need to know. So what they did was they broke down a human into 3 parts. So there's some perceptual input, so that's processing information from the eyes, information from other senses. How long does that take? What does that look like? What's the biology? What's the cognition involved? Then there's cognition as a whole. How do you process that information? How do you make decisions based on that information? How do you store and recall information? Is there a difference between whether you have perceived visual image versus an auditory sound? Is there a difference in how you process that? And then what is the output? So in this example here, you're going to press a button, but how long does it take for that, once you've made that decision, click, how long does it take for the brain to send that information through the nervous system to your finger to press the button? And so this, what we would now call the interaction cycle, this interaction cycle is the basis of this text, The Psychology of HCI. So it's a huge book, but there are parts of it that are very, very interesting. And within it, there's a summary of a few different laws or different things that we use when we're designing interfaces. So the first of those is Fitts law, and the idea that a larger target closer to the cursor is easier to hit than a smaller target further away. So I want you to imagine that I have my mouse and I'm trying to click on, let's say, the eye. So for me to click on the eye here is not super difficult, but if I want to click on the top tip of this arrow further away, that's obviously much more difficult. It's smaller and it's further away. So I will upload a separate video on Fitts law because it's an interesting and relevant thing, and we'll talk about it a bit more in the human factors section. Hicks law is about how do people make choices. So the reaction time to select something, a choice, increases logarithmically. So that means that it's increasing by a little and then more and more and more and more and more as the number of choices increases. So we can do things like say, we want someone to take no longer than X seconds to make a choice. How many choices can I give them? And so things like safety critical systems, this is really important, because if I am flying an aircraft and I have to choose between 6 things and I'm 3 feet off the ground, it's probably not going to end well. But if I have to make a decision between 2 things while I'm 3 feet off the ground, it's probably going to be much more successful for me and my aircraft. So we can use that law when it comes to things like information architecture. How do we arrange menus? How do we arrange buttons? And how do we arrange any kind of thing that we would select? Okay, so this is the first real compilation of a teaching text in HCI, the Psychology of HCI book. It's the first real recognition that this is no longer just about we can make technology do something. This is we can make technology do something, but we can't make people do the thing that we want. We have to recognize that people are biologically programmed to behave in certain ways, culturally programmed to behave in certain ways based on their psychology, and bring that into all of our design factors and design decisions when it comes to technology. And it's still used as a textbook in a lot of larger institutions that focus on the cognition and the psychology. Okay, moving on, we have the first Apple Macintosh 84, or the first commercially successful desktop computer. So it's the first time that we've managed. Remember, we had the Xerox, it wasn't successful, it had processing images. Really, what's different between this and the others? Hardware. The hardware is good. There's a massive marketing campaign around it. You know, obviously it's expensive. Who's going to buy it? But we have, spoiler alert, we have a mouse, we've got a keyboard, we've got space for some external storage devices, we've got that WIMP, what you see is what you get interface, and this is how it was introduced. So this is this completely random advert. This is how Apple introduced it to the world at the 1984 Super Bowl.
Today we celebrate the first glorious anniversary of the information purification directives. Created for the first time in all history a garden of pure ideology where each worker may bloom, secure from the pests, obeying contradictory rules. Unification of laws is more powerful a weapon than any fleet or army on earth. We are one people, with one will, one resolve, one cause. Our enemies shall force themselves to death, and we defy them with their own confusion. We shall prevail.
On January 24th, Apple Computer will introduce Macintosh, and you'll see why 1984 won't be like 1984.
So, super interesting play, and obviously the George Orwell book of 1984, but it's just funny what would have been a good advert in 84. If you put that on now, I'm not sure people would get it. Okay, so what does all of this mean? So, some time ago I asked students to write down what they think about what they think HCI is. And this is what I got from one of them. I got, who cares, it's the user's fault for being shit. And everybody laughed, right? Everyone went, oh, this person's an idiot, like, oh, they're so funny. Kind of ridiculing the topic, I suppose. But they're not far off, right? Because actually, one of the main textbooks that gets used for user-centered design, based on, we're taking the idea from the Psychology of HCI, that's our seminal psychology human factors book. We have this book, which is the Design of Everyday Things. So the Design of Everyday Things was written by Professor Don Norman in 1988, and it's all about the idea of affordance. So the affordance is the physical properties of an object that gives you clues about its function. So on the right we have the affordance of a handle is that you hold it. The affordance of a spout is that you pour it. I can't think of anyone that's going to pour a cup of tea out of that teapot, right? So you can use all of these cues, you can use all of the information you know, and it can still be a bad design. So he has a website which is the Design Lab. So he's currently an emeritus professor at the University of California, San Diego, and still has an office, still goes there just because he likes doing it. So Don Norman is like a great guy for all sorts of user-centered design and usability things. So this book, I recommend that everybody reads this book, especially if you're frustrated with technology, which hopefully a bunch of you are, because you're going around with your eyes open. You're going around with your eyes open and you're armed with knowledge about what it could be. But obviously you end up with poorly designed things, and it's not the person's fault. It's probably the person who designed it. And unfortunately, going forward, that's going to be you, right? You're going to be the people who are designing stuff. So, it's not the end of the world if it goes wrong, but, there are consequences, and it's nice to have a read of that and just kind of reflect upon how things are developed and why they're developed that way, and why we use societal and cultural norms in the way that we do. So, Don Norman has also hooked up with a guy called Jacob Nielsen, and Jacob Nielsen created 10 general principles for interface design. These general principles are pretty cool, and he's got a paper about why these are important, but also they're used as like an evaluation, right? So I can get any system and I can look at it and say, visibility of system status. Does it give me feedback about what's going on? So if you take the idea of Apple tends to have like a status bar that fills up the closer it gets to completing the action, and Windows has that kind of dial that just turns round and round and round and round, which gives me better visibility of the system status. Well, the Apple one, because it's telling me how much further I have to go as a proportion of what it's already done. I know whether I can sit here for a moment or whether it's worth going to make a cup of tea. So each of these systems, matching between the system and the real world, so that's using concepts that we are aware of, things that make sense to us, so what you see is what you get, desktop interface. When you're putting things, when you're deleting things, why do we use a bin icon? Because when we want to delete things from our lives, we put them in the bin. How do we prevent errors happening? So we prevent them happening by saying, see when you have menus and some items are grayed out, it's because that item's not possible, so it's preventing you making an error before you even do it. We let people undo, we give multiple exit points, and we have some flexibility and efficiency for use. So if you're an expert user, you're going to use something very differently than a novice user, and there is no place better to see that than self-service scanners in supermarkets. Like, honestly, even the first interaction will tell you whether someone is a novice or a new user, whether someone is confident in using the system and has discovered these shortcuts. Because they don't tell you you've got to discover them. You walk up, do you press the start button or do you just scan the first item? Straight away you know who has explored the system and who has perhaps made an error and realised that actually it's a shortcut, whatever it is. But that very first interaction, that person who scans the item first are going to have fewer problems than the person who stands and presses start. But some people need the start button, and that's okay. So these usability heuristics, what Jacob Nielsen did was he allows people to test new interfaces and discovers that actually you need a very small number of people in order to find a large number of problems. So actually doing user testing doesn't need to be expensive or time consuming, and you can use relatively untrained people to do it as well. So the link is there for the digital library. Go and download that paper and have a little look and see what you think. Okay, so if you want to read the Bush essay, the As We May Think, that's the reprint from 1996. It's in Interactions, which is the ACM magazine. And there's some detail there on just a further paper on computing for the 21st century. Again, from SIG Mobile, so that's another special interest group, but on mobile computing instead. Okay, so that is the history. But what is the future? What do we think of when we think of the future of HCI? So some of the things that you will read about in the CHI conference are very futuristic. So if we take what we consider to be an interface, it's no longer just a mouse and keyboard. We can have an interface which is completely invisible, so a voice interface. And we can have interfaces that are, invisible in terms of what they're placed on. So you can get a projector which projects a keyboard or a screen, like an Android type screen, onto any surface. And that interaction is one that we're familiar with, but on any surface, probably not. It's that ubiquitous nature of computing. If you think of like cookers, so on the kitchen worktop, there's hidden controls that we just don't know are there unless it's our house. What about your eyes? So your eyes are an interface. So we can currently use them to select things using an eye gaze system. But there was something in the news, or certainly in the tech news the other day, that they had managed to put a screen into a contact lens. And so yes, it is a very, very hidden interface, but it's also pretty cool. And what do we use to interact with it? Well, we use our hands, we use our voice, but can we also use other things? So can we use brainwaves as our output? Our output doesn't have to be clicking on something. But if we use our output in order to influence, we're making action with the technology, that's got to be considered as well. And how comfortable are people? So there's a social acceptability concept here. Am I happy to go walk around blinking and talking to my contact lenses? Maybe, maybe not. A lot of these kind of like augmented reality glasses, people are using them, but in what setting? Am I going out to Tesco with my HoloLens on? Probably not. But I know someone who uses it to subtitle because he's deaf. So he would go to Tesco with his HoloLens on and receive all the expected kind of strange reception that you would get if you went out with something that does look to the general public so futuristic. So for this guy, having a screen in his contact lenses would be amazing because it counters his disability and he can now have the world subtitled as he wants. So don't lose sight of that. So the point of the history is to give you an idea of where we are. But as we've moved on and technology has moved from a portable or a workplace computer, a room-sized computer, it's moved to a portable computer, it's moved from your traditional keyboard to a desktop interface. There's a mouse is developed. We now have direct manipulation and touch on like phones and tablets and so on. And so the space in which we're operating now is way bigger than improving a personal computer. And with that comes ethical and societal obligations. And at the back of your mind as we go through this course, I want you to have those ethical and societal implications in mind.